All them by the same place as it is. Set it so that you can test one of the instructors.
If they have left me out, they said, "Oh, this log is going to go."
Hi, so our first talk will be by Mrinal, and he'll be talking about high-rate multivariate polynomial evaluation course.
Thanks, Hargav. Thanks for the general introduction. And the reason I say this introduction is general is because last year when I was giving a talk in SQL Symposium, the session chair Pavel forgot my name. You can be better than that.
We are improving.
So I never have my name. But yeah. And at that point, I'd only shared an office space with Pavel for 6 months. So I'm going to talk about some, in my opinion, very clean algebraic questions about error correcting codes. There's a joint work with Swastik Kopati and Hari Shah at University of Toronto. So I don't know how many of you are familiar with codes, but this talk is supposed to be for everyone. So I'm going to tell you what, specifically focus on the kind of things we care about. But if there's something that you don't follow, stop me and ask questions. Most of this talk should be accessible to everyone. Okay. So let me start by defining polynomial evaluation codes. And so it's sort of a framework which works as follows. So there's some initial setup, and we are going to stick to this setup throughout. F is going to denote the field. D is going to be the degree of the polynomial we're going to work with. M is going to be the number of variables. And we will have a subset S of F to the n. So S is going to be a set of m tuples where each tuple has coordinates from the field F. And okay, so I'm not going to say why this is why I'm calling these messages, but the kind of objects we are going to be interested in are going to be m-variate polynomials with coefficients in the field F and the total degree being B. Is that okay? So these are m-variate. So m is the number of variables, so B is the total degree. And these messages, this is the space of messages, whatever that means, and these messages are going to be encoded. So these messages are going to be mapped to code words, where the code word corresponding to a message, so a message is a polynomial, the code word is just the evaluation of this polynomial on the set S of inputs. Okay, and since this is an m-variate polynomial, the set of entries in S has to be an m tuple over the underlying. Okay, everybody good so far? Right, so a message polynomial is going to be encoded by its evaluation vector on the set S. And clearly, the code words form a linear space over the underlying field, right? Because the messages form a linear space. So you can take the encodings of two polynomials, add them up, you get an encoding of the sum polynomial. Right? So there's a linear structure, so these code words form a linear space. Or in other words, this particular code is a linear code. Okay, and what's the dimension of this space, by the way? What should it equal? No, there's an answer written, but what does it mean in English? What is D plus n to them? It's the number of monomials of degree at most D on m variables. That's the dimension of the space of messages. That's also the dimension of the space of code. Okay, and in the setting that we are going to be in throughout this talk, think of m as being a constant, and think of D as being the growing parameter. Okay, so m is 1, 2, 3, 5, 10, something like that. D is growing. So D plus m choose m is roughly D to the m over n factorial. So far, so good? Okay, so let's summarize this. So two properties of such codes that we are going to be interested in are the distance of the code and the rate of the code. What does this mean? The distance of the code is just it's the smallest number of agreements between, or rather, I should have said the smallest number of disagreements between any two distinct code words. Okay, or in other words, I think this is correct. So it's the minimum number of non-zeros in any non-zero code word. And the code words are just the evaluation of polynomials over a set S. So the distance of the code corresponds to the smallest number of non-zeros that any non-zero polynomial can have over the set S. Okay, there's a typo in the first line. Don't worry about that. So generally, for when we construct codes like this, the distance of the code follows from choosing the set S with some desired properties. And the property typically for ensuring good distance is that the set S is constructed in such a way that no non-zero degree polynomial has too many zeros in the set S. Okay. And yeah, so throughout this talk, when I say distance, I really mean fractional distance. So minimum distance divided by the size of the set S. So I'll say distance 0.1. It means 0.1 fraction non-zeros on the set. So far, so good. Questions?
So you say m is a constant?
M is going to be a constant. Okay. The other property of these codes that we are going to be talking about is the rate of the code. And the rate of the code is just the definition is that it's the dimension of the code word space, which we know is b plus m chosen. It's the ratio of the code word dimension of the code word space and the ambient space. The ambient space is size of S dimension. So the rate of the code is just yeah. So the code word space is roughly d to the m over m dimensional, and the ambient space is size of S dimensional. So the rate of the code is d to the m over m factorial times S. Okay. I'll give you some examples, but is the setup clear so far? Questions on the setup? So the things that we have seen so far is that, so the definition of a polynomial evaluation code, this is just, we take degree polynomials on n variables, we evaluate them on a set S of inputs in the underlying domain. The distance of the code is this code is the minimum number of non-zeros any non-zero polynomial must have on the set S. And the rate of the code is d to the m over m factorial divided by S. The size of S.
There's some assumption about the size of the also.
Yeah, so good point. So I mean, so think of F as being some large finite field, or in fact, you could even think of this as being an infinite field if you don't care too much about the coding theoretic complications. So F should be large enough. If F is tiny, then many of these things. Okay, so to summarize, so this particular code where the message space is a set of all polynomials of degree d and variables with coefficients in F, the encoding function will just map a polynomial to its evaluations. This is a linear code, has dimension d to the m over m factorial. And the distance of this code comes out of some statement about a non-zero polynomial not having too many zeros in the set S. So that's the summary of everything we have talked about. And the rate has this expression that will keep coming up again and again. Okay, and in this talk, like I said, so we are going to be interested in the setting where d is growing, m is a constant, and I would like the rate and the distance, so the fractional distance also to be constant. So we would like codes such that this quantity is a constant, meaning size of S is roughly some constant times d to the m over m factorial. And no non-zero degree d polynomial has more than a constant fraction of 0. This constant could be something. So think of 0.1 fraction. Every non-zero, I want a set S so that every non-zero degree d polynomial has at least 0.1 fraction non-zeros on the set. Okay, so let's take some examples. So the most famous example of codes like this are the Reed-Solomon codes, which is the setting when m is equal to 1. We are working with univariate polynomials of degree d. So the message space is that. The encoding is just going to be the evaluation of this polynomial on the set S. This is clearly a linear code. The dimension is d plus 1 because we are looking at degree d univariate. It has d plus 1 coefficients. And the distance of this code is roughly 1 minus t over n. And the rate is d plus 1 over n. Okay, same formulas that we had previously. And the rate plus the sum of the rate and the distance is roughly 1. And codes of this kind are they are said to be these are codes that are said to live on what is called the singleton bound. So these are optimal codes in some sense out there. Okay, questions? All right. So the main protagonist of this particular talk are what are going to be called Reed-Muller codes. So these are polynomial evaluation codes when the number of variables is more than 1. Okay, and here the set S that we usually take is a product set. So it's a set of Cartesian. You take a set T of the underlying field F of size n, and you take the Cartesian product of T with itself n times. Okay, so it's a grid. If you want to visualize it in 2 dimensions, it's a grid. And here the messages are m-variate polynomials of total degree d. The encoding is just the evaluation on this grid. The distance of this code is also equal to the distance of the Reed-Solomon code that we saw previously. Why is this? This is because of the Schwarzschild lemma. Okay, I won't tell you what the lemma is if you haven't seen it, but Google for it. So the distance of the code is 1 minus d over n, and the dimension of the code is exactly what we noticed earlier. So the rate of the code is d to the m over m factorial times size of s. Size of s is n to the m. So this is d to the m over n to the m times m factorial. If I massage this, so I can write this as d over n to the m, and d over n is 1 minus delta. So the rate of this code is 1 over n factorial times 1 minus delta to the m. Everybody good so far? Okay. So the thing to notice here is that if delta is a constant, so think of delta as being 0.1, which means d over n is 0.9. The rate becomes 0.9 to the m divided by n factorial. Okay. So if the distance happens to be constant, the rate is inverse exponential in n. Okay.
Why would one use the then why would you do that?
Why would we use right, exactly. But even for m equals 2, that's going to be an interesting section for us.
But then why would n?
Good point. So there may be other features, other properties of these codes that may be useful. For instance, as m grows, these codes become more and more local. Sometimes we care about the locality. Yeah, but you're right. I mean, if I want to construct codes where all I care about is the rate distance trade-off, then I'll probably stick to Reed-Solomon codes and not code. Okay, so that's the setup. So the question that we're going to be interested in is to understand if there exist polynomial evaluation codes where I can get constant distance and rate close to 1. I want the distance to be a constant, but I don't want my rate to fall as m grows. So even for m equals 2, if you take delta to be a constant, then the rate is 1 over 2 times 1 minus delta 1 minus delta squared. So there is a factor 2 in the denominator, which means the rate cannot exceed half. Okay, so the cleanest question really that I'll talk about here is, can we construct polynomial evaluation codes in 2 dimensions, where the distance is a constant, the relative distance is constant, and the rate is arbitrarily close to 1. So I want rate 0.99. Reed-Muller codes are not given. Okay, questions? So far? All right, is the question clear to everyone? Okay, yeah, I mean, this is some, this is the m equals 2 case discussed in more detail, but yeah, I mean, the question we care about is about here. So we want constant distance and rate vector. Okay, so I mean, I've said so much about polynomial evaluation codes so far, but why do we care about polynomial evaluation codes? So what is so special about it? So they seem to play an outsized role in both coding theory and its connections to computer science and to math. Let me justify it a little bit. So applications to probabilistically checkable proofs, interactive proofs, pseudo-randomness, algorithm design, topography, algebraic complexity, and this is an incomplete list. Polynomial evaluation codes show up in all of these things in very, very fundamental way. There are applications in extremal combinatorics, convex geometry, like if you have heard of the finite field Takaya problem or the decoding problem. And if you haven't, you should go back and check. And polynomial evaluation codes play a very fundamental role in all those things. In addition to these black box applications where we just use some basic black box properties of the underlying code, there have been sort of more subjective advances in our state of understanding of various problems across areas when we try to understand properties of polynomial evaluation codes. And these insights have sort of had applications in algebraic property testing and algebraic algorithms. And lastly, but I think most importantly, constructing high-rate polynomial evaluation code, it's a very natural question about low-degree polynomials. And if we strip all coding theoretic jargon from it, this is the question. Can we construct small sets of points where a non-zero polynomial doesn't have too many steps? And in a very, very sort of fundamental sense, this is an important question in this generality. and something that we don't fully understand yet. Yeah, so it's like that in some sense.
So, yeah. So should we think of this as a way of stripping away monomials, or should we think of it as a way of reducing the set of points on which?
I mean, I think of it as keeping the space as it is, so we are not stripping away monomials. So the space, the message space is always going to be all degree polynomials on m variables. But yeah, I mean, you should think of it as the latter, where we try to construct smaller and smaller sets which guarantee that a constant fraction of non-zeros will be witnessed. Other questions?
We want sets where the Schwarzschild lemma will not just grids, but
Yeah.
still continue to hold.
Yeah, or maybe something better than Schwarzschild. Okay, so let me mention the results. So earlier this year we showed that. Okay, so take m to be a constant and take any epsilon greater than 0. So think of epsilon as 0.1, m as being 5, 10, 20 something. And if the underlying field has sufficiently large size or sufficiently large characteristic, there are two constructions. One of them requires large size, the other requires large characteristic as well. But yeah, and so I mean, for all it's worth, think of this as being a large prime finite field. There are explicit polynomial evaluation codes for m-variate polynomials whose rate is 1 minus epsilon. So rate is epsilon close to 1. And the relative distance is some constant that depends on epsilon. Is the statement clear? Questions? All right. Yeah, so there are two constructions. One of them will require the field size to be large, the other will require the characteristic also to be large. I will sort of tell you what the constructions are. I won't prove things about it. So there are two explicit families. We have names for them. The first one I'm going to call cap codes. So these are combinatorial arrays of polynomials. When I show you the definition, you'll see why this is a reasonable name, or not an awesome name. And the others we are going to call gap codes. So they are at Hamming distance 1 from each other, the names, but they have different properties. Okay, so the first construction is going to be some combinatorial construction of a set of points where every non-zero degree polynomial has a constant fraction of non-zeros. The second construction is going to be a geometric construction of such points. Hence the names. Okay, so in addition to explicitly constructing such point sets, we also show that both these codes, gap and cap codes, can actually be efficiently decoded from less than when the number of errors is less than half their minimum distance. So this is sort of the unique decoding regime of codes. We would ideally like codes that are decodable in this sense. These codes happen to have these problems. Even for polynomial evaluation codes, having polynomial evaluation codes that can be efficiently decoded from up to half their minimum distance is not something we can take for granted. For instance, Reed-Muller codes that have been studied since the 1950s were only shown to be uniquely decodable in this sense less than 10 years back. So even though this seems like a very natural statement if you come up with a good construction, it's not something we can take for granted.
So how, for example, if m was not a constant,
yeah,
and if it was growing, what would happen?
Yeah, so you have you continue to have the distance continues to be inverse exponential in n. Okay.
Is like epsilon to the power 1 over n, or
epsilon to the n, 1 over epsilon to the n. Okay. 1 over epsilon to the n.
the distance of the number less than 1.
Oh, sorry. I mean epsilon to the n. So it will take 30 seconds to come with the exact expression, but I'm blacking right now. Okay. Other questions so far? All right. So let me show you what these constructions are. And they're sort of clean and nice constructions. In fact, some of you in the audience will recognize one of the constructions because of a homework problem I gave last year. Okay, so I mean, like I said, these constructions are going to be based on designing a small set of points such that every non-zero degree polynomial has a constant fraction of non-zeros on the set. And For cap codes, the point set is going to look like a simplex. So I'll say more on the next slide what this means. And for gap codes, this is going to come out of this point set is going to come out of intersection of hyperplanes in general position. I will say more on what that means in a moment. Okay, both these set of points are not new. They have been known to be hitting sets for low degree polynomials, meaning that it's known that these point sets constructed in both these constructions are places where a non-zero polynomial cannot vanish entirely. It can't be zero everywhere. It has to have at least one non-zero. And what we end up showing is that it will not just have one non-zero, it will actually have a constant fraction of non-zero, quite a few non-zero. Okay, and showing that this is a hitting set was a homework problem for some of the people in the audience a year ago. Okay, so let me say what cap codes are. So suppose that you have a field of large characteristic, how large? Larger than the degree of the polynomial, so larger than t, and m is equal to 2. So I'm going to only consider m equals 2. So let me define the set S sub k, which is the pair of points I comma j. So that I is between 0 to k, j is between 0 to k, and the sum of I and j is at most k. Okay. The size of the set Sk is clearly k plus 2 choose 2. What does this set look like? Triangle. Yeah. So as you can see in this, this picture took me a long time to draw, but it is a triangle. So this is it's a simplex in 2 dimensions. And something that Blazer and Pandey showed about maybe 7-8 years back is that no non-zero polynomial of degree k can vanish entirely on Sk. Okay. And in fact, something more is true. So the set of points is what is called an interpolating set for such polynomial. If you know what that means, that's good. If you don't, that's okay. I don't intend to say more. But what we show is that instead of evaluating a polynomial of degree k on Sk, if you evaluate a polynomial of degree 0.9 k on Sk, take the degree to be a little bit less than a constant fraction less than k, then you will actually see a lot of numbers. You will see roughly 10 to the minus 3 numbers. Okay. So this is the first construction.
What you said about Mrinal, vanishes on more than a very small fraction.
No non-zero polynomial vanishes on more than. This is correct.
That's what you said. You said there was 1 minus 3. No.
Oh no, this is what I mean. Constant fraction non-zero, some tiny constant, but a constant fraction.
The distance is 1 minus.
The distance is actually. Okay, wait. Now I'm confused. So no non-zero polynomial is vanishes on.
Oh, yeah, so it should be less than.
Yeah, you're right.
Less than 1.
Yeah, and then there should be 1 minus point.
And it should be less than.
It should be less than. No, more than. More than is fine. Nothing vanishes on more than 99% of this point. Okay, fine. You know what I mean. Yeah. So, all right. Yeah. So the code is just we will take bivariate polynomials of degree 0.9k, evaluate it on the set Sk, and the rate of the code is 0.81 if you do the calculations, and the distance will be from the statement that I had here, which is incorrect. Okay, let's move on to gap codes. So let me define what. So I'm going to focus on 2 dimensions. I said this is a set of points that comes out of taking intersection of hyperplanes in general. So in 2 dimensions, hyperplanes are just lines. What does it mean to say that a bunch of lines is in general position? It means that every pair of lines will intersect at a point, and no 3 lines are concurrent. Okay. So take the set G sub k to be the set of evaluation points. So these are going to be pairwise intersection of k plus 2 lines in general position. So we take k plus 2 lines in a plane in general position, take their pairwise intersections. This is the set G sub k, and the same paper of Blazer and Pandey that I mentioned earlier shows that if you take a degree k polynomial that is non-zero in two variables, it doesn't vanish entirely on the set G sub k. Which means that, yeah, in fact, again, this is an interpolating set. And what we show is the strengthening of this theorem where we actually prove that, okay, again, so no non-zero polynomial of degree 0.9k vanishes on more than 1 minus 0.0001 fraction. So there exists constant fraction non-zero. Okay, so what does lines in general position mean? So here is a construction. I will not prove that these are general position, but it's not hard. So take the set of lines that are the equations are of the following form. So we pick an alpha I from the underlying field and we look at x plus alpha I y plus alpha I square. We take the I, so we pick a bunch of distinct alpha i's from the field F. That's why we need the field to be large. And we collect the following lines and then we take the pairwise intersections. You can actually show that they are in general position. It's an easy exercise. Any two intersect, no three are concurrent, and yeah, all you need is the alpha is to be distinct, which needs the field to be large enough. And in m dimensions, you take hyperplanes in m dimensions, which are in general position. So what that means is that every set of m hyperplanes intersect at exactly a point, and no set of m plus 1 hyperplanes intersect. And as you can see, so in high dimensions, this point set has some inherent geometric structure in it. And this ends up being useful for giving us some local properties about the scope. I don't know how much I have. Okay, so maybe yeah, we'll get to locality. All right, so the minimum distance of this code. So the proof of this is sort of a more general connection between hitting sets and distance of the corresponding polynomial evaluation code. So it's a statement of the type that if you give me a set of points where no polynomial vanishes entirely, then you can do something similar to get a more robust statement on the same set of evaluation points. So maybe I have a statement here. So the lemma is that if you take a set S, that's a hitting set for degree capital D m-variate polynomials, and you decide to evaluate m-variate polynomials of degree little d on it. So remember the sets Sk and Gk were hitting sets for degree k polynomials. And when we constructed the code, we evaluated polynomials of degree 0.9k on it. So capital D is like k, little d is like 0.9k. Then it will have, that set is guaranteed to give us at least these many non-zeros. Okay, and if you are in the setting that m is a constant, and capital D and little d are sort of within a constant fraction of each other, we get the kind of scale. Okay, so this is how both the constructions go. We had earlier proofs which were far more complicated and tailored to each of the constructions, but eventually this is what happens. So we have a pretty clean argument for this. And this is via what's called the polynomial method, if you know what it is. Okay. I'm not going to say anything more than this. Let me say something about unique decoding. So the unique decoding algorithms here actually end up being considerably, at least for gap codes, they end up being considerably cleaner and simpler than what it was for Reed-Muller codes that we knew about. So they're based on ideas from Forney's decoder. This is a very famous set of results in coding theory, and some recent work around it. Like Kim Koparty's unique decoder for Reed-Muller codes that I earlier mentioned. So for cap codes, this is like ideas in Kim Koparty together with an analysis of Forney that showed up in a recent paper of Prahlad, Siddharth Bhandari, Ashutosh, and myself. And for cap codes, this argument is even cleaner. We can sort of, essentially we view cap codes as some sort of concatenated codes and gap codes as some sort of concatenated codes, and we sort of get a very clean, unique decoder for. Okay, if you're not familiar with coding theory, this slide would not make sense. But
Concatenated means one.
Yeah, like you take an outer code, replacing symbol by. Okay, so
On the unique decoding. So typically these are used as outer codes.
Yeah.
These objects. Reed-Solomon, one advantage of using it as an outer code, it works with both erasures and errors. Will all of these also work?
I suspect so, because we end up using error erasure type things in both of them.
Okay.
But I don't know for sure, but I
Because what that would mean there's a subset of this set of points also.
yeah, that gives you right.
It's also a good.
Okay.
Yeah.
Okay, so I mentioned this local structure mysteriously earlier. Let me say what that means. So this is this notion of a code being locally testable. What that really means is the kind of questions we want to understand is the following. So suppose we are given a received word, so we're given a word F, and the goal is to decide if F is close to a code word from your favorite code or is it really far from. Again, close and far in having distance. So for instance, if I want to talk about local testability of gap codes, I'm given a function F, is it close to a code word, a valid code word of gap code, or is it like very far? Very far meaning constant fraction far. And local testing are algorithms that answer this question by only reading a few coordinates of the code word. You don't want to read the whole thing and decide this. You want to read a few coordinates, sample a few coordinates, read it, and just make this decision. And it's a really important notion in general, although it's not a very old notion. Certainly for the broad area of property testing, but one of the reasons for sort of central importance of polynomial evaluation codes and Reed-Muller codes, in particular in computer science. So PCP is cryptography, pseudo-randomness, algorithm design, etc., is their local testability. But these local testability results for each solvent codes rely on the fact that the evaluation point is the entire field. So you evaluate the code, the message, the polynomials on F to the n, the entire field. And the analysis of many of these local testability algorithms are of inherent interest. They tend to yield new information about the structure of low-degree polynomials over a field. So for instance, local testability of Reed-Muller codes, it just follows from, so it's the following setup. You're given a function f from f to the m to f, that's how we view it, and view this as sort of an oracle access where I'm going to query f at some inputs. I don't want to read the whole thing. And I want to understand if this is close to a degree D polynomial or it's far from every such polynomial. And a typical test will just query the function on a set of points that corresponds to a line or a set of points that corresponds to a plane and does various things. Okay, so for instance, the line point test will pick a random line and a point x on the line L and then check something very simple, like it will accept if the degree D polynomial, univariate polynomial closest to f on the line agrees with f at the point x. And the kind of things we care about here is the query complexity. So how many points are we going to query? How many inputs are we going to read the function f? And this has been analyzed in various settings, so classical results like Rubenfeld-Sudan, Polishuk-Spillman, Friedel-Sudan, Arola-Sudan, recent work, etc., etc. But one of the things that really sort of seems to play an important role in these analysis of local testing algorithms is that the underlying set of points is a field or a subfield or has some rich algebraic structure. For arbitrary product sets, so Reed-Muller codes, when I defined them, I didn't say you have to take the set S to be the entire domain. You could take it to be an arbitrary product set to get distance from the short-zipper lemma there. Far limited, and there are some recent results only within the last year on this. So for gap codes, we show that gap codes are actually locally testable by the line point test and the plane point test. So for the line point test, we need the rate to be somewhat small. We can't deal with rate close to 1. But for the plane point test, these codes are locally testable with rate arbitrarily close to 1. And in addition to being yet another family of polynomial evaluation codes with local testability, I think this result to me is a little surprising. And the reason is that the set of evaluation points on which where a gap code works could be some really tiny set of points living in a large space. Right? We take a set of hyperplanes in general position, evaluate the polynomial. So you could even ask this question over rational numbers. So where you have an infinite ambient space and you have some evaluation of low-degree polynomials on really small set of points in some corner, and you can actually locally test. So this is a bit surprising. All right, and what this proof uses is the inherent geometric structure present in the point set. So it uses some high-dimensional geometric structure that comes up inherently because of the construction of the code. Okay, so let me start with some open problems. So one thing that would be nice to do is to construct high rate code, or even constant rate polynomial evaluation codes when the number of variables is growing. So we don't know how to. When the number of variables grows, all our everything that we do seems to break down. What we have is a unique decoding algorithm for gap codes and gap codes. We don't have efficient list decoding algorithm. There are some technical issues here, but I think it'd be nice to understand anyway. The other question that has been open and is passed around a little bit is to construct list decoding algorithms for Reed-Muller codes on arbitrary product sets. So now we are in the regime of parameters where the amount of error that I am allowed to introduce in the received word is more than half the memo distance of the code, which means that the closest code word is no longer unique. And for many nice codes, we have good, efficient, clean list decoding algorithm. But for Reed-Muller codes on arbitrary product sets, which is one of the most studied codes going around in all of coding theory, we do not have list decoding algorithm that are efficient. And it'd be nice to have applications of these codes. So in particular, the local testing results, we suspect will have applications, but we don't know anything about it. Let me stop.
Questions? You know anything about local decoding?
So these codes I don't think are locally decoded, but there may be variations of these that could be. But I'm not sure. I suspect they are not locally decoded. I think there's not enough locality in that sense to be decoded. Other question?
What is it's called gap.
Oh, that construction was combinatorial.
So combo.
Yeah, I mean, if it was about the shape of the points, we would call it hat codes, but it's not. The construction and the earlier proofs we had were very, very combinatorial. So the final proofs look good. Other questions?
Okay, let's end the speaker.